In this video, we're just going to look at a couple of examples of how we can make Maclaurin polynomials faster using some of the ones that you should have memorized. So the first question, find the 8th degree Maclaurin polynomial and the general term for e to the x squared. Well, first, again, you should probably be moving towards memorizing that e to the x is approximated by this general term is x to the n over n factorial. So e to the x squared, every time we see an x, we should just replace it with this x squared. So maybe I'll put my work down here. E to the x squared, this would be approximated by 1 plus x squared plus, now x squared squared is x to the 4th. And then we have x squared cubed, that's x to the 6th. And then we have x squared to the 4th, that would be x to the 8th. So the expectation here is not that you would actually find 8 derivatives. You know, it says 8th degree. What you would have done before is found 8 derivatives and gone through. You don't have to do that here. You should be able to just substitute it into the known series and go until you get to your x to the 8th. So my general term is going to be x squared to the n over n factorial, which of course we could even better write as x to the 2n over n factorial, like that. Okay. Now next, we've got sine. Now again, let's look at sine real quick. Sine, that series, or that approximation, goes x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. It's alternating, so we've got a negative 1 to the n, and it's x to the 2n plus 1, and then I'm kind of out of room here. It's 2n plus 1 factorial, like that, because it's the odds. Now, again, you know, it says find the 21st degree. We definitely don't want to find 21 derivatives here. So we have two things going on in this particular series. We've got x to the 4th in place of x, and we're multiplying by x. So let's start with just replacing every x with x to the 4th. Let's say that the sine of x to the 4th, that would be x to the 4th minus x to the 4th cubed is x to the 12th, and then x to the 4th to the 5th is x to the 20th, like that, okay, dot, dot, dot. So now, if I'm really going to multiply by x, right, I'm multiplying this function by x, well, this is algebraic. If I do it to one side, I just do it to the other as well, like that. So I end up with x to the 5th minus x to the 13th over 3 factorial plus x to the 21st over 5 factorial. So you can see it only took 3 terms. You say, well, find the 21st degree polynomial. Seems like it's going to be a lot of terms. It turns out to only be 3. So my general term, we had negative 1 to the n. That's not going to change. It's still alternating. Instead of x to the 2n plus 1, it's x to the 4th to the 2n plus 1 all over 2n plus 1 factorial. That wasn't affected. And then we multiplied by an additional x. So if you simplified this, you'd have negative 1 to the n, x to the 8n plus 4, and then another x. You'd have x to the 8n plus 5 all over 2n plus 1 factorial, like that. Now, one question I didn't put on here, but I kind of wish I had, is what is the value of the 21st derivative of f at 0? And again, some people will look at that and say, oh my gosh, do I really have to find 21 derivatives? The answer is no. What you need to remember is that in a Maclaurin or Taylor series, a 21st derivative, when divided by 21 factorial, gives the coefficient for the x to the 21st term. Well, take a look at this. We have the x to the 21st term, and the coefficient is 1 over 5 factorial. So, again, go back to what we know. To get coefficients, we take a derivative, we divide it by 21 factorial, and that's equal, in this case, to 1 over 5 factorial, because that is the coefficient on the x to the 21st term. Again, let me just say this one more time. If I want to find a coefficient, specifically in this case the 21st power, x to the 21st, the way we've always done this in series is we take a derivative divided by n factorial, so the nth derivative divided by n factorial, and that goes with the x to the nth term. So when I say I want the 21st derivative, I need to look, what's the coefficient on the x to the 21st term? And it was 1 over 5 factorial. So the answer here, when we multiply, is just 21 factorial divided by 5 factorial. That is the value of the 21st derivative. Okay? Now, the other thing I guess I should mention, a lot of times people will look at this and they'll say, well, what happened to all the other terms? You know, sine used to, I understand it, you know, with the x squared over 2 factorial, that term, that coefficient was 0. But, you know, we built that one. What happened to all of these? The x to the 6th, x to the 7th, and so on. Well, the answer is all of those coefficients, all of those derivatives must have been equal to 0. The 6th derivative, the 7th derivative, 8th, and so on. Anytime we have a term missing, that means that the derivative must have been 0. Okay? Now, finally, what are all the values for which this infinite series converges? Well, this is just a little limit comparison test. And n over n to the p, the power has to actually be greater than 2. Because remember, if it were equal to 2, this by limit comparison would be 1 over n, and that would diverge. And this little question here, we have a product. Substitution won't work, so we go to integration by parts. And in this case, we could even use, you know, our old tic-tac-toe method, the anti-6x. So antiderivative of sine is negative cosine. Put that 1/6 up front. Antiderivative, we got negative 1/36 sine. Positive, negative. So I should see a negative x over 6 cosine 6x, and then minus a negative, so it is this one.